right. Hi, everyone. I'm José Valim. Thank you. People watch the video later and they say, like, why are they laughing by just saying his name? This would be good. All right, so in the program, this talk was originally called Announcing Broadway, but I think that instead of just announcing Broadway and say how you use it, you can go check the documentation. We care a lot about documentation. We wrote a lot of good docs, a lot of guides on that. So today what I want to focus on is actually on the road that took us to Broadway. And it's interesting because when I was working on this talk, it's a very long journey. We were on this journey for like 6-7 years, and I was able to get slides from a bunch of previous presentations to build this one. So it's funny because I have the slides here that I used in my first ElixirConf talks back in 2014, 2015, right here at this conference center. Right, so this talk is about this journey that I have been on. But before I go into the journey, I just want to, if you're curious, what is Broadway, right? Or maybe you have a plane to catch and you want to leave as soon as possible, I'm going to give a very quick introduction to Broadway. So Broadway is a new library for concurrent and multi-stage data ingestion and data processing with Elixir. So what is the problem that we're trying to solve? Imagine, for example, that you have data on Amazon SQS or on Google Cloud PubSub or RabbitMQ, Apache Kafka, right? And you want to process this data, right? And if you're doing that with Elixir, you want to process this data most likely concurrently and as efficiently as possible. So you get this data, you can send it to a bunch of workers, right, that are working on this data. And then, for example, if you're using Amazon SQS, after you work on this data, you have to batch it because that's the most efficient way, both in terms of money and time, to acknowledge that the data has been processed to Amazon SQS, right? Or maybe you just write into another store, and it's most efficient to do that, creating batches as well. So you may want to batch the data, and then finally you publish this data after you batch it, right? You're going to publish and acknowledge this data. Who here has a similar problem or is working on data pipelines, data ingestions in any kind of way? Can be in any language, right? Great. So with Broadway, we are making this really, really easy with Elixir, really accessible, really simple, because all you have to do all of this is to define all this amount of code. So you say, I have a module, I want to use Broadway, and then you have to implement 3 functions. You have to implement start link, handle message, and handle batch. And handle message is where you're writing your code. You're already writing your business logic. You don't have to worry about anything else. So you say, oh, here's what I want to do with each message. And then handle batch is what you do for each of those batches. And start link, the implementation is straightforward. All that you do is that you call Broadway start link, passing the module that you're going to, that have all those callbacks. And then you say, look, I have producers, right? And for this example, I'm getting data out of SQS. This is my queue name. And I want to have 4 stages. I want to have 4 things getting data out of SQS at the same time. And then you say, I want to have 20 processors. So they're all processing each individual event message, 20 at the same time. And then finally, you want to create those batches. And here we're specifying, look, I want to create batches of 10 messages, right? 10 events. And if by any chance, I can't put 10 events, 10 messages in a batch in 1.5 seconds. I want to send the batch with how many elements I have in there, right? So you can control the batch either by its size or the time that you are allowed until you go to that limit. And then once I'm going to have 2 batchers, 2 things that are publishing those messages back. And that's it, right? Then you go there, you write your business logic, you write your code, and you run it in production. This is great, right? So this is what you can do with Broadway. But in order to get to Broadway, as I said, there was a very long journey. And that's what I want to talk about. So we are going to talk about collections. We're going to talk about GenStage. And we're going to talk about Broadway. So I want to ask 3 questions. So who here is using Elixir? Please raise your hands. Right, so collections. Who is here using GenStage or use GenStage? Great. And has somebody already used Broadway? A very early adopter? It's out last week. I think there's a hand in there. Kinda. You read the docs and built a prototype. Yes. Beautiful. All right, so let's get started. Collections. So when I created Elixir, or actually not even that. So Elixir started as a fun project. I like to say that nobody has a problem and they say, oh, I know I'm going to solve this problem. I'm going to create a new programming language, right? Because like, good luck, you just gave yourself like 10 years of work. So, so Elixir started as a fun project. I do not have a formal computer science background. I wanted to understand how programming language work. So I decided to how I can implement my own. And I was a little bit familiar with the Erlang virtual machine, so I was like, well, I may as well implement it for the Erlang virtual machine, and then I can kind of like learn two things at the same time, or improve at two things at the same time. And then I did, and as Bruce showed, I had like that prototype stage at the beginning, and then it was bad in all different kinds of ways. So I had like the valley of despair, where I was not working on Elixir itself. But throughout that time, I was thinking, you know what, maybe there is an opportunity here for creating a programming language that runs on top of the Erlang virtual machine that provides a different feature set, a different way to write software compared to the language we had at the time, mostly Erlang. So I built on this idea. I started thinking about this. I did a bunch of research. And I did define some features, or I had some ideas for things that I wanted to have in Elixir, right? And that I think are very important. That will be the foundation for Elixir. And some of those, we talk a lot about it, like metaprogramming, right? Or using Erlang as the main abstraction, right? Like not going too far away from Erlang. So I had that. But one of the most important things that we don't get to talk a lot about it, that is really important for Elixir, is that we decided to have a strong focus on data types. And there is an important class of data types that we use every day, which are the collections. And I wanted to have, Bruce referred to it in when he was telling the story as well, and I wanted to have a unified approach to collections, right? So with time, we built a list of requirements. We said, look, I want collections to be polymorphic. And so what are collections? Lists, sets, queues, maps, dictionaries, right? So I said, I want collections to be polymorphic, which means that instead of, if we have like 20 different collections, I do not want to have 20 different modules, each working for each collection type, right? I want to have a unique API that can work across all of those collections, right? So it should be polymorphic. It should accept many shapes, right? All the shapes. So that was one. I also want the collections to be open, to be extensible. And what I mean by that is that if Elixir ships with some collections as part of its standard library, and we have the enum module to work with those collections, and if you are in your project, right, and you define your own collection, you should be able to teach Elixir how to work with our collection as well, and how to traverse our collection. And that's what I mean by extensible. Any data type, any collection that is implemented in the future should work with whatever mechanism we come up with. We also want it to be general. So we wanted to work with lists, sets, maps, and collections that we have in memory. But we also wanted to work with resources like files. So you should be able to traverse a file using the API that we have to work with collections. And finally, for lack of a better word, I want it to be tunable. I want to be able to have a pipeline that is working with collections, and then by default it's eager, but if I want, I can make it lazy, I can make it concurrent, I can make it distributed. I should have a path to go through this journey. And we're actually able to implement a lot of those requirements. I'm not going to go in the technical details today in this presentation, but I wrote a blog post called Introducing Redundancies. So the way we were able to solve this problem, as Bruce said, we are based on an idea from the Haskell community called iteratives. But if we implemented iteratives as is for the Erlang virtual machine, it would not be super efficient. So we changed a couple things around, and that led us to redundancies. And that's the abstraction you can read more about on this blog post. But what I want to do for this talk is that I want to explore how those requirements translate to us developers as users of Elixir, right? So polymorphism, right? This is polymorphism. I can call a nummap passing a list, right? And then I multiply every element in it by 2, or I can pass it a range, and it all works. It's also extensible. And why is it extensible? Let me roll back here a little bit. So the module that we use to work with collections in Elixir is the num module, right? And as we see here, it's polymorphic, but it's also extensible because behind the scenes, the num module calls the enumerable protocol. And protocol, it can be implemented at any time for any data structure. So if you have your own collection like a red-black tree, you can just implement the enumerable protocol, and now Elixir can work with our collection as well. Collections, they are also general, so we can say, look, I have a list of lines, for example, a list of strings, and I want to upcase each string in there. But if the list of lines is in a file, right, I can just say, look, I have a file stream, right? And what that is going to do is that it's going to take care of opening the file for you, giving you line by line in the most efficient way as possible. And then if there is an error, or if you get to the end of the collection, we close the resource for you. We take all the burden of doing the resource management or moving the cursors in the file. We do all of it for you. You don't have to worry about it. And we're able to make it partially tunable, right? So we're able to go from eager to lazy, and I want to show you how. So collections in Elixir, they are eager because Elixir is an eager strict language. And what this means is that if I have a list 1, 2, 3, and then I call a nummap passing a print function, what print does is that it prints the number and returns the number itself. So you can see that if I have the list 1, 2, 3, call a nummap with print, and then call a nummap with print again, you can see that it prints 1, 2, 3, 1, 2, 3, and then returns the list with those numbers, right, with the original numbers, because we're returning the number as is. And in Elixir, this is eager, right? Like at the moment you call a nummap, we traverse the whole collection, right? We traverse the whole list and build a new whole list. And then we call a nummap again that is going to traverse the whole list and return the whole list again. And in Elixir, we can make this lazy by replacing enum by string. So you just replace enum by string, and now we made it lazy. And here we can already see the first difference. Instead of executing the code, it just returns a string because the string is lazy. It's not going to do any work until you ask it to, right? And one of the ways that you can make the stream work is to actually make it eager, is to realize it. So you can say stream run, or you can say I want to convert the stream to a list. And now you can see that instead of printing 1, 2, 3, 1, 2, 3, it prints 1, 1, 2, 2, 3, 3. And why is that? It's because the string, it doesn't traverse the list multiple times. When you say stream map, what it does is that it fuses all of those computations, right? It creates a recipe, right, on how you want to process the collection. So it fuses all those computations, and then instead of traversing the collection multiple times, we get the first element and then perform our computations. And then we get the second element and perform all the computations again. And why this is important? This is important because it allows us to work with really large collections. Imagine, for example, you have a 1 GB CSV file that you have to process. If we use a num, you have to load the 1 GB into memory, and then you process it, and then you process it. All of the 1 GB in memory, it's going to generate a lot of garbage, right? With string, we never load the whole 1 GB into memory. We get the first line, we process it. We get the next line, we process it, and so on and so on. And this is exactly the feature set that made into Elixir 1.0. Okay? So if we look at this journey, we're able to get like reasonably far in this journey. We got polymorphism, we got extensibility, it's general, and we can go from eager to lazy. And then after Elixir 1.0 was out, we rested a little bit, and then we're like, you know what? We are ready for the next step. We are ready to go now from lazy to concurrent. And we started working on that. And our first implementation of this feature, our first prototype, was inspired a lot on reactive extensions from .NET. So imagine that you have a pipeline here where you have a file stream, which is, for example, you can imagine that here is a CSV processing pipeline, right? So you have a file stream, and then you want to like map over each line, like breaking on the comma, and then you do another operation. So each pipe with the 3 dots represents an operation. Our first approach is, well, what if I could introduce something like stream async And every time you call stream async, it means that all the operations before it or above it is going to happen in a separate process, right? So it's going to happen concurrently, right? So if I have this pipeline and I add all those stream async calls, we are going to have something like this, where you have the file that sends the data to another process, that sends the data to another process, and so on, until you get to the end of the thing and you get your result. It turns out that this approach is bad for a couple different reasons. So the first one is that it is error prone, right? Because it's the developer that has to add the stream async, right? The developer needs to go there, oh, I'm going to put one here, another one here, right? And then maybe the developer is going to optimize it by hand on their machine. But you're going to run in production, and that may have different performance characteristics, right? So it can be all wrong, right? The other thing that is bad about this is that if we are creating multiple processes to do data processing, how do we communicate between those processes? By sending messages, right? And every time we send a message, we are copying the data. So if you use stream async too much, you could actually have a performance slowdown, right? Because we are spending most of the time moving the data around. And now that we are thinking about processes, and here's particularly where I think the Erlang virtual machine made me a better software developer, because now that we are talking about concurrency, we are talking about processes. Every time you create a process, you should ask yourself the question, what is going to happen if this process crashes? So we started to think, yeah, like I have a pipeline that is processing data. What happens if something here in the middle of the pipeline crashes? So we started to think about fault tolerance. The Jose from the past would probably just implement the feature and be happy and not consider fault tolerance at any moment, right? Another thing is that, again, since we're talking about processes and we are sending messages between processes, when you send a message to another process, that message goes to that process inbox, to that process message queue. And the message queue is unbounded. So what happens if we have if we have one step in the pipeline that is slow, right, and is being flooded with messages, and it cannot catch up, right? You can eventually maybe run out of memory, right? So we started to think, you know what, we started to think about all of those things, and it became clear that the way we were approaching the problem was wrong, okay? We're thinking about the stream, the data aspect first, but we realized that we should actually think about this process first. So we started to think, well, we're probably going to need a new abstraction, like we have a Gen server, which is for client server. We have GenState M, which is about state machines. We probably need to have a new abstraction, which is about exchanging data between processes. And we did 2 other prototypes. We actually had funny names where we tried to things like we had the Gen router, we had a Gen broker. So if you go back, like watch very old presentations, we actually talk about those. And those all had limitations in a couple different ways. And then in our 3rd or 4th iteration, we ended up with GenStage, okay? So that was the first part of the talk, just really talking about collections and how we really had a focus on having a unified approach when we were talking about working with data. And then eventually, as we explored, it led us to GenStage. So what is GenStage, right? Let's go to the next part. What is GenStage? It's a new behavior. It's actually old today, but it's a new behavior. And the idea with GenStage is that it can exchange data between stages transparently and with back pressure. And we have 3 kinds of stages. We have producers, which are the sources. We have consumers, which are the sink. And we have producer-consumers that are in the middle. So here's how a GenStage pipeline could look like, right? Have a producer, and then it sends data to the producer-consumer, and so on, until you get to the sink, which is the consumer. The cool part of GenStage, is that everything is demand-driven. The producer cannot go and say, hey, here's data, and start sending data to the consumer. That's not possible. Actually, so there is actually a conversation here. So the first thing that it happens is that the consumer subscribes to the producer, right? And then after the consumer subscribes, it can send demand. It can say, hey, give me 10 events, right? And then after the consumer sends the demand, the producer can send those events. And it can send it in any way it wants. It can send all 10 at once. It can send 1 by 1, 2 by 2, but it cannot exceed 10, okay? And the nice thing about being demand-driven is that we can push the demand to the boundary of the system. right? So for example, imagine that you have like now 3 stages. What is going to happen is that C is going to ask B for 10, B is going to ask A for 10, and then eventually A is going to send those, and B is going to send those. So what is really nice about this is that we push this demand, we push this back pressure to the boundary of the system, to the producer, because the producer is the one that is going to be getting data from the external system. And you don't want to get more data than you can chew, more data than you can handle, right? So we are going all the way up and say like, this is how much I need, this is how much I can work with right now. So being demand-driven, it pushes back pressure to the boundary of the system. And it's just a message contract. And behind the scenes, they're just regular process messages. And GenStage is one of the implementations of this contract. So if you, for some reason, you don't like the GenStage API, you can implement your own. As long as it obeys that message contract, everything is going to work just fine. And it's very inspired by AccuStreams. I want to thank Konrad Malawski from the AccuStreams team. He was extremely supportive with feedback, providing ideas, suggestions, and so on. All right, so let's see an example how all this would work. So let's use a very simple example where we have 2 processes here, 2 stages. We have a counter that is a producer. You can think that is going to just count 0, 1, 2, 3, up to infinity. So every time somebody asks an event, it's going to start counting up and emitting those events. And we have a consumer, which is a printer, and all it does is to print the batch of events it receives. So here's how we would write a producer. We say, look, I have a module. I want to use GenStage. And as usual with processes, we have to implement the init callback. And the init callback receives the counter, the initial value we're going to start counting from. We say that it is a producer. And then the other callback that we need to implement is handle demand. And handle demand is invoked every time a consumer asks data. So a consumer say, hey, give me 10. Handle demand is going to be called with 10, right? It's going to be called with the demand of 10 and the counter. So what we do is that we produce events from the counter, from our state, up to the demand, and return the events in the updated state. So that's an example. Imagine that we start with a state of 0, right? And then somebody asks for 10 events. What we do is that we're going to return a list of events from 0 up to 9, giving exactly 10 events. And then we update our state to 10. And then now the state's 10, and then somebody asks for 5. And then you say, OK, here's 10, 11, 12, 13, 14, right? And then you update your state again, and you go so on and so on. All right, and how does the consumer look like? Like this, you'll say, look, I have a consumer. I want to use GenStage, but now on init, instead of saying I'm a producer, I say that I'm a consumer. And the consumer does not care about the state, so I'm just passing a random atom here. And now instead of implementing handle event, you implement instead of implementing handle demand, you implement handle events. And what we are doing here is that we are sleeping for a second in order to simulate work. And then we inspect all the events, and we return no reply so we can process the next batch. So this is the code, and now we just have to wire everything together. So what we do is that we can start the producer, which is the counter. We can start the consumer, which is the printer. And then we say, hey, consumer, printer, I want you to subscribe to the producer, which is the counter. And after you do this, you're going to wait a second, and you're going to see the events being printed from 0 up to 499, exactly 500 events. And then you wait another second, and then you get 500 more. So you can see here that in our code, we did not have to worry about any of the asking, any of the managing who is receiving the events. GenStage takes care of all of it for you, right? Don't have to worry about that. But you may be wondering, all right, that's awesome, but why 500 events? What is happening here? So this actually happens. This can be controlled for the subscribe options. And what are the subscribe options? We have max demand, and this is the maximum amount of events to ask. And it defaults to 1,000. Then we have the minimum demand, which is the value that when reached, we ask for more events. And the default is half of maximum demand. That's why we're seeing 500. Okay? And then there's the cancel option that tells you what is going to happen if that subscription, what is going to happen to the consumer if that subscription terminates for some reason. Either because the producer crashed or the producer said, hey, I'm not producing more events. So you can say if you want, what you want to happen, and the default is that then the consumer crashes. I want to talk a little bit about why it's very important for us to have maximum demand and minimum demand. And in order to do that, let's consider this example. Let's say that we have maximum demand of 10 and a minimum demand of 0. What is going to happen? So the consumer, as we saw, asks for 10 events, right? And then the consumer receives those 10 events. The consumer is going to process those 10 events. And then what is going to happen here is that the consumer is going to ask for 10 more. And then the consumer has to wait, right? Because it received a batch of things to do. It did everything it could do on that batch, and then asked for more. And now all the consumer can do is wait, right? This is not good, right? Because we have a consumer there idle, right? Ideally, the consumer is going to be working all the time. And that's why we have the minimum demand, and the default is half, because in this case, this is what happens. The consumer asks for 10 items. The consumer receives those 10 items. The consumer now, because the consumer knows that as soon as it reaches 5 items, it can ask for more. It says, look, I'm going to process only 5 out of those 10. And then after it does that, it asks for 5 more. And then while the producer is producing those 5 extra ones, the consumer is processing the remaining ones. So assuming the producer is fast enough, the consumer is always working. Great, this is great. So there's one last thing I want to talk about GenStage, which are the GenStage dispatchers, all right? So what are the dispatchers? It's something that we configure per producer. It effectively receives the demand and the sending of the data. So remember how I said that in our code in that example, we don't have to manage like for asking data and receiving the data, everything works transparently. This is because of the dispatchers. That's the job of the dispatchers. And the dispatchers are important because they enable concurrency by dispatching to multiple stages. So right now, we just saw a single pipeline, like producer, producer, consumer, producer, consumer, producer, consumer, consumer at the end, right? What we actually want to have is this. We want to have one producer and multiple consumers, right? All of them processing data at the same time, right? And the default way we do this is that we have a demand dispatcher. And the demand dispatcher works by sending data to the process that has the highest demand. So imagine, for example, you have the events 1, 2, 3, 4, 5. You can imagine that at the beginning, you're going to send the first event to the first, the second to the second, the third to the fourth, the third to the third, the fourth to the fourth. And then imagine that in this example, the second consumer here was able to consume its event, the event that it received faster. So that's the one receiving 5. We also have a BroadcastDispatcher that dispatch the events to all the consumers. And we have a PartitionDispatcher that routes the events to the consumers based on a partitioning function, on a given function. And so we worked on this, and we announced it on the Elixir blog. We announced GenStage. This was back in July 2016. And a lot of companies started using GenStage in production, right? We saw a show of hands here. Discord, for example, they're using GenStage to handle bursts of over 1 million push requests per minute. We have the folks from Adro. They re-engineered part of their data processing pipeline. And then at the end, they added Flow, which is built on top of GenStage. And they were able to reach a solution that was already improved. And when they started using Flow as well, they were able to get twice the throughput that they had before. There is also this very good case from, we don't have their logo here, but from Football Addicts. They have to send push notifications because they are about sports. So if somebody scores a goal, for example, they send a bunch of push notifications, right? And they're using HTTP2 to send those push notifications, and with GenStage, and they are able to send 1.3 million notifications in a 10 seconds period, right? So a bunch of very exciting use case of GenStage. And what happens is that what we saw is that a lot of the companies using GenStage, they were using it for the same purpose, which is data ingestion and data processing, right? So after we put GenStage out, we started talking to the community. Myself from Plataforma Tech, we were working with clients and different companies. We started to see this use case happening over and over again, right? And what we saw is that, everyone doing data ingestion, data processing, is that they're using GenStage exactly to get concurrency and the back pressure. But we also saw that many projects, they were implementing the same feature set, rate limiting, batching, metrics over and over again. And we also saw that many of the projects, they were struggling on a similar set of issues, which is how they're going to set up complex data processing pipelines, right? And this is the last thing I want to talk about before we go talk about Broadway per se. So imagine that maybe after this talk, or maybe you saw the GenStage presentation almost 3 years ago, you said, all right, this is great. I'm going to implement my own data ingestion, data processing pipeline. So you start implementing it. So the first thing that you do is that it starts simple, right? Because it always starts simple. If it starts complex, then that's really worrying. So yeah, so what you do is like, look, I'm going to have a producer, for example, that gets data out of RabbitMQ or whatever. So I'm going to have a producer, and for now, I'm going to have a single consumer, okay? So you put that under a supervision tree, right? You say I have the producer, I have the consumer, they are supervised one for one, so if one crashes, only that thing's restarted. So you put them in a supervision tree, start really simple. The producer is getting the data, the consumer is handling it, and then you're like, great, you put this in production, everything works, and then like, we are ready for the next step, right? Which is, let's have multiple consumers. So you start with the producer, and then you have now 4 consumers, because that's the goal you wanted to achieve. You wanted to process data concurrently, right? And this is when you make your first mistake, right? Because you added the consumers, and you didn't reevaluate the supervision strategy. So what happens in this case is that if the producer crashes, all of the consumers, they're going to crash as well, because they are linked through the subscription. And so what's going to happen is that if the producer crashes, all the consumers crash as well, and then the supervisor like, oh my God, all my children are dying, right? And then the supervisor is likely going to go over the maximum restarts value of the supervisor. Then the supervisor is like, I have to restart myself. And this is fine, because it's going to go up in your supervision tree, and then your supervision tree is going to restart the whole thing. But you want to avoid that if possible. So you do the first change, like you do the first fix, right? You say, okay, I'll change the strategy from one for one to rest for one, right? And then you run this in production, because now if the producer crashes, the supervisor is already expecting all of the consumers to crash as well. So the supervisor will be like, okay, this is good enough. And it has one downside for this particular implementation, which is if the consumer in the middle crashes, the consumers after it is going to crash as well. But they're like, you know what, it's good enough. There are other ways to solve this problem, but it's good enough. And this is what we recommend in our docs. All right, so then you're like, running this in production, it's much better. And then you're like, all right, so now I think we are maxing out the consumers. Let's have 2 producers now and more consumers, right? So you do this change. And then now the rest for one strategy does not work anymore. Why? Because if the first producer crashes, it's going to shut down everything, including the second producer. But they are independent, right? The first producer should not bring the other producer down. And now we don't even want this behavior anymore, where one producer brings the consumers down, because the consumers could be processing data for the other producer that did not crash. So you have to reevaluate the whole thing again, and then you probably do the thing that you should have done since the beginning, which is to have a supervisor for each layer, okay? And then you do write this code. It's just complexity that you have to manage, but you do write this code, and then in the future you add more processing steps here in the middle, right? So the complexity is growing, right? And then we are still not done, though, because what is going to happen when you shut down a node? When you say, hey, for example, you're doing a deployment, so you're shutting down the existing nodes, you're going to start new ones. What is going to happen? When you tell the airline virtual machine to shut down, it goes through all the supervision trees and say, hey, you should shut down. And what happens is that the supervisor is going to shut down the processes in the opposite order that they are started, right? So here we're starting the producer first, because we want the consumer to subscribe to the producer, right? So the producer has to be there. So we start the producer first, which means that the first ones to terminate is the consumer, right? But this is very bad for our data processing pipeline, right? Because imagine that you have a bunch of stages, right? And if the consumer is the first one that terminates, you have a bunch of data here in the middle that will never get into the end, right? So what we have to do is that you have to implement one solution here, is that you implement a terminator T3000 process that its job is just to wait, right? It waits there when the supervisor says, hey, we are shutting everything down. The terminator says, hold on, I have some work to do, right? It trap exists to say I have some work to do, right? And then it goes to the producer and say, look, the first thing that you're going to do is that you have to stop accepting demand. If somebody asks you for more events, like, don't listen, just ignore. And this is part of the GenStage API. It's one function call, but you have to do it. And you have to do that for all producers. And after you do that, you have to tell, hey, producers, what you also have to do is that now you have to flush all the events that you may potentially have. And after you flush all the events, let me know. Right? So the producer does that, all the producer does that, the terminator receives those messages, and then after all the producers flushed, the terminator can go to the next process, to the next layer, right? And then can go all for the producer consumers, and then it does that for all the layers until it gets to the consumers and say, hey consumers, I want you to flush, and after you flush all the events, let me know. And then after all the consumers terminate, the terminator is like, all right, supervisor, the data has been drained from the pipeline. You can now shut down all of the processes. Right? So when we're talking about complex GenStage pipelines, we have to think about how to structure supervision trees correctly, how to handle graceful shutdown without data loss, how to reduce the amount of events lost during failures. Right? You have to handle all of this. If you have a GenStage pipeline in production and you have not thought about those questions, you don't have to panic. Right? Why? Because, for example, if you're getting data from Amazon SQS, right, what is going to happen is that if you lose some data, it's going to go to a dead letter queue, and you're going to process it again. Most well-designed data processing pipelines, they are idempotent. So if you have to replace some step again, it's not going to change the overall result. Right? But if at some moment you and your team are like, we want to design this correctly per the spec, right? You have to waste a lot of energy and brain cycles on how to solve this problem. And we saw a bunch of different companies, a bunch of different teams working about those things, going out to different conclusions, sometimes making the same mistakes over and over again. And this is exactly what led us to Broadway, right? So the idea with Broadway is that we have implemented all of this for you, hopefully correctly. So you don't have to do that over and over again anymore. So let's review what is Broadway, okay? So as we said, Broadway is a new library for concurrent and multi-stage because we are using GenStage, right? A new library for concurrent and multi-stage data ingestion and data processing with Elixir. And why is it called Broadway? It's because we have stages, producers, so yeah. And what do you get if you use Broadway today, right? You get back pressure and concurrency, exactly because it's built on top of GenStage. You get automatic acknowledgements at the end of the pipeline. So if you're using SQS, you don't have to go and say, hey, SQS, I'm done. We take care of it for you. And if something fails, we're going to send that as a failure. Everything's taken care for you. Fault tolerance with minimal data loss, right? And I was told that the combination of words here, minimal data loss, is a bit scary. Right? But it's minimal data loss because, for example, if somebody pulls the plug in the machine, right, or you're doing something really bad that leads to a segmentation fault in a bad NIF, you're going to lose data, right? There's only a certain amount that we can do, but within Broadway, you are safe. So fault tolerance with minimal data loss. Graceful shutdown. So implement a terminator T3000. It's there, right, to do the job for you. Batching and partitioning. So we do all this. And you get all these by just implementing those three functions. That's all you need to do. And we're already working on we're already thinking about the next features that we want. So what we want to support is batchless pipeline. So today you have to do batching, but there are like some data sources like RabbitMQ that does not actually require you to batch to acknowledge the data in batches. So we want to allow you to, we want to make the batching optional if you want to. We want to have built-in metrics and statistics. We want to provide automatic back-off in case of failures, and rate limiting, a bunch of other features. All right, so we have working on this for since October, so last 4 or 5 months, right? And now it's the perfect time for you to get started. So what can you do? You can give Broadway a try. So version 0.1 was released last week, so it's beta software. Right, still very early, but if you want to give it a try, the feedback's very, very welcome. You can also write a Broadway producer for your favorite thing. Right now, we ship with Broadway SQS. Okay, we are working as well now on the Rabbit MQ1. So, and if you have your own favorite thing, you can write a Broadway producer for that. But if you already have an established pipeline, you have already your own GenStage producer, and you want to use Broadway, you can do that as well. You can bring any GenStage producer and put that as part of Broadway. All right, and finally, I want to thank Platform Attack. So Elixir was born as a research and development project inside Platform Attack. And we have a bunch of other projects, and Broadway is the latest project coming out from our research and development team. This project is being led by Marlus, so a huge thank you to Marlus as well. And that's all I had to share for today. I'll take some questions now. Thank you.